We've talked a lot about electrophilic aromatic substitution reactions where the benzene ring is the actual functional group that undergoes the reaction. In this video, we're going to talk about a few other reactions of aromatic compounds where the reaction doesn't happen on the ring, but the ring influences the reactivity. So the first example of this is oxidation. Here we have an alkane 2-methylpropane, and this can be treated with sodium dichromate and sulfuric acid. This is a source of chromic acid, and this can also be used to oxidize a primary alcohol to a carboxylic acid. But here we don't have an alcohol, we just have an alkane, and so if we treat it with these conditions, we get no reaction. Okay, that's not very exciting. But if we take toluene, so here we have benzene connected to a methyl group, if we treat this with sodium or potassium dichromate and sulfuric acid, in this case, we are going to make benzoic acid. So this methyl group is oxidized to a carboxylic acid. What if we have benzene connected to a longer alkyl chain? Well, we still end up making benzoic acid. We don't have to worry about the mechanism of this reaction. If you're interested in it, I'm sure we can find it, but I just want you to know that the benzylic position is going to be oxidized to the carboxylic acid. The rest of these carbons are also going to get oxidized, but they're much smaller pieces, and so they're going to be separated. Think about your time in lab. They're going to be separated in the aqueous layer, whereas we're going to focus on this in the organic layer, for example. Now, in our final example, if we have T-butylbenzene and we treat it with chromic acid, we get no reaction. So what's necessary here? Okay, we have to have benzene. If there's just the alkyl positions, then we get no reaction. But with benzene next to it, what do we have here? This is a benzylic position, and we have, in this case, 3 benzylic hydrogens. Here we have 1 benzylic hydrogen, and in both these cases the reaction works. Here there are no benzylic hydrogens, and there's no reaction. So side chain oxidation using chromic acid requires at least 1 benzylic hydrogen, and it gives the product of benzoic acid. No matter whether we're talking about a 1-carbon side chain or a 50-carbon side chain, it is the benzylic position that is converted to the carboxylic acid. In addition to using chromic acid, we can also use potassium permanganate in water followed by HCl. These conditions are going to behave the same way. No reaction with an alkane, reaction with any compound that has at least 1 benzylic hydrogen, again giving benzoic acid. No reaction if there is no benzylic hydrogen. Here we have a few other examples of important reactions of aromatic compounds, and once again we're focusing on the benzylic position. If we have benzyl bromide and we treat it with a strong base such as methoxide, this is going to carry out SN2 substitution, leading to this product. So it's SN2, the nucleophile attacks, in this case, the benzylic carbon, pushing away bromine as a leaving group. If we were instead to use the same starting material, but we treat it with methanol, this is a primary and benzylic halide, but this is a very, very, very weak base. So this controls the type of substitution reaction. If we have an alkoxide, it can do SN2, but if we have the alcohol, it can only do SN1. Now, a regular primary alkyl halide would not do SN1 because it can't form the carbocation. But this is primary and benzylic, and so a benzylic carbocation is stabilized by resonance. Therefore, the benzylic carbocation can be formed, followed by nucleophilic attack by methanol, followed by an acid-base reaction, leading to this ether as the final product. Here is another example where we have a bromide and then we want the methyl ether. So again, this is a substitution. This one is benzylic and tertiary, so we definitely cannot use methoxide because it's way too crowded. This will give elimination rather than substitution. So instead, we can use methanol to carry out an SN1 substitution. And another example, if we have isopropyl benzene and we want to substitute a bromine at this position, what are we trying to do here? We have a hydrogen and we want to replace it with a bromine. We're not talking about a nucleophilic substitution. We are trying to replace a hydrogen. So think about radical reactions. What we want to do is generate bromine radicals, which can then abstract a hydrogen atom preferentially from the benzylic position because this benzylic radical is stabilized by resonance into the benzene ring. And this radical can react with more bromine to give this product, and it generates more bromine radical, which can continue the chain reaction. So to do a radical halogenation at the benzylic position, we could use bromine and light and or heat, or we can use the specialized reagent NBS and bromosuccinimide along with peroxides or heat. So when it comes to aromatic compounds, we have a number of reactions that can be carried out on the benzene ring itself, but we also have other important reactions that can be carried out at the benzylic position. Being able to put these reactions together enables us to carry out multi-step synthesis where we can predict and control the products that we obtain.